In this section, we generalize the idea of conditioning a random variable by an event to conditioning pairs of random variables. In this case, we'll get a conditional joint PMF and a conditional joint PDF, depending on if the random variables are discrete or continuous. The natural starting point is the conditional joint PMF of x and y given some event b. On the left side, we have a function of the dummy variables, little x and little y. And on the right side, we have the conditional probability that x equals x and y equals y given the event b. Before conditioning, we thought of x and y as a pair of random variables with the joint PMF p of xy. Now we have x and y given b as a new distribution on those x's and y's. From the definition of conditional probability, we can write this as the probability of the joint event, x equals x, y equals y, and b, whatever b happens to be, divided by the probability of b. When b is shorthand for the event that the pair xy belongs to b, that is, that b is a region of the xy plane, we can continue and write that this event we can think of as, oh, x and y equal x and y, and x and y belong to the set B over P of B. And in this numerator, we see that if x and y simply are little x and little y, right, then either little x and little y belong to the set B or they don't belong to the set B. And if they don't belong to the set B, then this joint event has zero probability. That is, there are two cases to consider. The first case is that x and y pair belongs to the set B, and in this case, the numerator is simply equal to the probability x is x and y is y. And of course, the denominator is still P of B. The other case is that x and y do not belong to the set B, and in that case, the numerator probability has to be 0. In fact, we just derived the main result for the conditional joint PMF of x and y given B. The idea here is that the points that belong to B have their probability scaled up by 1 over P of B, and the points that don't belong to B have now 0 probability. Here's a simple example to demonstrate the theorem. We have the joint PMF on the left defined on the integer points that make up the triangle, and we add the condition B that x plus y is less than or equal to 4. To find the conditional PMF, we first find the region B. And the region B consists of all points below this blue line where x plus y equals 4. By the theorem, we have the conditional PMF of x and y given B is equal to the original PMF of x and y divided by P of B for x and y belonging to B and 0 otherwise. All that's left in this problem is to identify those points x and y that belong to B that also have probability that's strictly greater than 0. And those points are pretty easily seen to be the 4 points that the PMF is non-zero that lie below the line x plus y equals 4. From those 4 points, we know that P of B is equal to the sum over all x and y belonging to B of the PMF of x and y. And that's simply equal to the 4 points that were given the red coloring. we add up those probabilities, and that equals 7/12. And then applying our theorem, we obtain that the conditional PMF of xy given b of x and y is equal to 1/4 divided by 7/12, which equals 3/7 at xy equals 1, 1. 1/8 over 7/12, which is equal to 3/14 at xy equals 2, 1, and also 2, 2, and 1/12 over 7/12, which is equal to 1/12 at xy equals 3, 1, and 0 otherwise. In short, what happens is that the conditioning on B picks out all the xy points with non-zero probability that are also in the set B, in that case these 4 points in the triangle, and scales their probabilities so they add up to 1. The definition of the conditional joint PDF for a pair of random variables xy acts in the same way. Points xy that belong to the conditioning event B, that density, the density function over those points is scaled up by 1 over P of B. Points xy that don't belong to the set B then have density that's 0. The result is that the conditional PDF of x and y given B is a density function that integrates to 1 over the set B. In this example, the joint PDF of x and y is uniform over the box where x goes from 0 to 5 and y goes from 0 to 3. In this problem, you're asked to find the conditional PDF given the event B that x plus y is greater than or equal to 4. The solution appears on the next slide, and it's a little bit ugly because the intersection of the region B and the region where the joint PDF is non-zero is kind of an ugly region. So just for fun, let's consider an alternate problem where instead of x plus y greater than or equal to 4, let's consider x plus y less than or equal to 3. In this case, we have the xy region, and x's go from 0 to 5, y goes from 0 to 3, and inside of this box, the joint PDF of x and y is equal to 1/15. And now we have the conditioning event B that says x plus y is less than or equal to 3, and that corresponds to this line, which is the line where x plus y equals 3, and then the conditioning says that we have to be below this line. Normally, we would find P of B by integrating the joint PDF over the triangle, but in this case, because the PDF is uniform, we know that P of B is equal to 1/15 times the area of the triangle, which is equal to 1/2 the base 3 times the height 3, and this is equal to 9 over 30, which is equal to 3/10. The joint PDF of x and y given B is simply equal to the joint PDF of x and y divided by P of B for x's and y's belonging to B and 0 otherwise. And this is equal to 1/15 divided by 3/10, which is equal to 2/9 for x and y satisfying x greater than or equal to 0, y greater than or equal to 0, and x plus y less than or equal to 3. and 0 otherwise. In short, what happened is that the density of points in the blue region was scaled up so that the PDF integrates to 1 over that triangle. Here's the solution to the original problem, with B being the region that x plus y is greater than or equal to 4. In this case, we mark the line where x plus y equals 4, and then we know that x plus y has to be above that line. And the intersection of the region B and the region where the joint PDF is non-zero is the dark gray shaded area that we're highlighting once again. And what the problem does is it calculates that P of B associated with x and y being in that funny shaped region, and then it does exactly the same thing that it did before. It took the old PDF and normalized it by P of B, and arrived at a uniform PDF over the region B. When W is a function of both x and y, we can again define the expected value of W. In this case, the expected value of W given the event B, right? It's exactly the same as the way we did the calculation of the expected value of W before, but instead of using the ordinary PMF PXY or PDF P of X, F of XY, we instead use the conditional PMF or conditional PDF. At this point, you might be wondering, why are we conditioning on regions, such as B, where x plus y is less than or equal to 4? Why don't we consider simpler kinds of conditioning, like B is equal to x equals 4? And the answer is that in the discrete case, a condition like B that x equals 4 is straightforward and can be handled. But in the case of a continuous random variable, the event x equals 4 has 0 probability. And we have to be a little bit more careful in our derivations. You'll see this in your next lecture.